Hello chemistry students, Dr. Tellis here again, and in this section we will describe nuclear chain reactions, nuclear fission, and nuclear fusion. So back in 1938, two chemists, Hahn and Strassmann, isolated and identified barium in a sample of uranium that had been bombarded with neutrons. How was barium formed? The answer? That the uranium nucleus had split into smaller pieces in a process we now call nuclear fission. Was one of the most significant scientific discoveries in the 20th century. The details of nuclear fission was unraveled through a work of a number of scientists, but they determined that uranium-235 nucleus initially captured a neutron to form uranium-236. This isotope then underwent nuclear fission to produce two new nuclei, one that had a mass around 140 and the other with a mass around 90, along with several neutrons. The nuclear reactions that led to formation of barium when a sample of uranium-235 was bombarded with neutrons is as follows. Here's my uranium-235. It captured a neutron to form uranium-236. This uranium-236 then underwent fission to form barium, has a mass of around 140, which is 141, and krypton. There's that mass of around 90, and 3 neutrons. Nuclear fission is a nuclear reaction where a heavy nucleus splits into lighter nuclei and releases energy. This process is highly exothermic. It produces about 2 times 10 to the 10th kilojoules of energy per mole. And this process sometimes occurs spontaneously, like with californium-252. We can see that this process breaks into 2 smaller nuclei and 4 neutrons. An important aspect of fission reactions is that they produce more neutrons than are used to initiate the process. So under the right circumstances, these neutrons then serve to continue the reaction. If one or more of these neutrons is captured by another uranium-235 nucleus, a further reaction can occur, releasing even more neutrons. This sequence repeats over and over. This mechanism, where each step generates a reactant to continue the reaction, is called a chain reaction. A nuclear fission chain reaction has 3 general steps. Number 1 is initiation. The reaction of a single atom is needed to start the chain. Following the absorption of a neutron to form uranium-236, the reaction is initiated by decomposition of that atom. Number 2, propagation. Absorption of neutrons and splitting of uranium atoms repeats over and over, with each step yielding more product. The fission of uranium-236 releases neutrons that initiate the fission of other uranium atoms. And then termination. Eventually, the chain will end. Termination could occur if the reactant, that uranium-235, is used up, or if the neutrons that continue the chain escape from the sample without being captured by that uranium-235. Here are a couple of visualizations showing fission. Let's look at the energy of nuclear reactions. Nuclear reactions involve changes of energy on a much larger scale than what occur in chemical reactions. This energy is used in nuclear power reactors and can provide the energy for nuclear weapons. Currently, there are about 54 nuclear power plants and 96 reactors in the United States, powering tens of millions of homes and communities, and about 440 nuclear power plants worldwide. About 17% of the world's energy comes from nuclear power. Here's a little chart showing different countries and how much power comes from nuclear energy in those countries. Here's a schematic of a nuclear power plant. A nuclear reactor uses the energy that's generated by fission as heat. To harness the energy, it's necessary to control the rate at which a fission reaction occurs. This is managed by balancing the propagation and the termination steps to limiting the number of neutrons available. This is accomplished by using cadmium rods to absorb neutrons in a nuclear reactor. By withdrawing or inserting the rods, the number of neutrons available to propagate the chain can be changed. and the rate of the fission reaction and the rate of energy production can be increased or decreased. The heat from the fission reaction is used to generate steam, which in turn powers the turbine. And that steam that is going to power this turbine then is converted into electricity. And what's neat about nuclear power, all of that steam that condenses on a cooling coil then turns into liquid water, which is expelled into, let's say, a river or a lake. So the byproduct of nuclear energy is water. Although one might imagine that nuclear energy would be called upon to meet the ever-increasing needs of society, there is a reluctance to move in this direction. Among other things, the disasters at Chernobyl in the former Soviet Union in 1986, 3 Mile Island in Pennsylvania in 1979, and Fukushima power plant in Japan, which was damaged by a tsunami in 2011, they've all sensitized the public to the issue of safety. Also, the cost to construct a nuclear power plant is considerably more than the cost for a natural gas-powered facility, and there are severe regulatory restrictions. Disposal of highly radioactive nuclear waste is yet another thorny problem, with 20 metric tons of waste being generated per year at each reactor. In addition to technical problems, nuclear energy production brings with it significant geopolitical security concerns. The process for enriching uranium for use in a reactor is the same process used for generated weapon-grade uranium. Also, some nuclear reactors are designed so that one byproduct of their operation is the isotope plutonium-239, which can be removed and used in a nuclear weapon. But despite these problems, nuclear fission is an important part of the energy profile in a number of countries. For example, about 75% of power production in France and 25% in Japan is nuclear power generated. In nuclear fusion, several small nuclei react to form a larger nucleus and generate tremendous amounts of energy. An example is the fusion of deuterium and tritium nuclei, so hydrogen 1 and hydrogen 2 to form a helium nucleus and an energetic neutron. This is the reaction that provides the energy of our sun and other stars. Scientists have long dreamed of being able to harness fusion to provide power. To do so, a temperature of 10 to the 6th to 10 to the 7th Kelvin, like that in the interior of the sun, would be required to bring the positively charged nuclei together with enough energy to overcome nuclear repulsions. At the very high temperatures needed for a fusion reaction, matter does not exist as atoms or molecules. Instead, matter is in the form of a plasma made up of unbound nuclei and electrons. 3 critical requirements must be met before nuclear fusion could become a viable energy source. First, the temperature must be high enough for fusion to occur. Second, the plasma must be confined long enough to release a net output of energy. And third, the energy must be recovered in some usable form. Now, harnessing a nuclear fusion reaction for a peaceful use has not been yet achieved. Nevertheless, many attractive features encourage continuing research in this field. The hydrogen used as fuel is cheap and available in almost unlimited amounts. As a further benefit, most radioisotopes produced by fusion have short half-lives, so they remain a radiation hazard for only a short time. Fun fact that every second, 600 million tons of hydrogen are being converted into helium by the sun. This reaction releases a tremendous amount of heat and energy.